All right, this is a continuation of Chapter 11 from OpenStax, and the chapter is on solutions. Now, in order to understand properties of solutions, we have to know what's in the solution. In particular, do we have an electrolyte or a non-electrolyte? And if we have an electrolyte, do we have a strong, a weak, and then again, a nice non-electrolyte? All right, to understand electrolytes, we have to remember what electrolytes are. Electrolytes are going to be ions in solution, in particular in water. And ions in water are going to allow electricity. Electricity is a flow of charged particles. Now, I know in physics we think of electricity as flow of electrons, which is perfectly valid, but it can also be a flow of charged particles. For example, a flow of things like sodium. So we have a couple of kinds. We have non-electrolytes. Non-electrolytes have no ions. These would be molecules in water. We can have strong electrolytes. Strong electrolytes are going to have lots of ions, and these are going to be things that are soluble. Back from Chem 111 when we looked at our solubility rules. These are going to be compounds containing sodium or potassium, going to be nice and soluble and give us lots of ions. We can also have weak electrolytes. Weak electrolytes are going to have just a few ions. When we have a few ions, our classic examples on this are going to be weak acids and weak bases. And we're going to consider this further along as we get into our acids and bases chapter. So, what have we got? We have non-electrolytes, molecules in water. Strong electrolytes, lots of ions, lots of electricity, lots of charged particles. And we have weak electrolytes, just a few ions, and those would be our weak acids and bases. So how does this work? Well, what happens if we have something like potassium chloride, KCl, and our KCl starts out with this as a solid, and we have some water that we're going to put it in contact with. They do not stay separated. Our water separates so that we have separate molecules of water, and as it separates, it is going to grab the potassiums and the chlorides and separate them so that we have potassiums in water, we have chlorides in water, and then once these guys are separate, they can move, and if they can move, we can have charged particles moving in water, which is electricity. All right, factors affecting solubility. Factors that affect solubility can be the structure of the molecule. We can have the pressure, in particular if we have a gas over a liquid such as water. The pressure of the gas over the liquid strongly affects the solubility of it. And then temperature. For a lot of solids, as the temperature goes up, the solubility goes up. For gases, as the temperature goes up, the solubility is going to go down. So let's discuss this in detail. Things that can affect its solubility. Classic example on this are vitamins. Vitamins that have a lot of polar groups in them, for example, hydroxides. For example, vitamin C. Vitamin C actually contains many acids on its end. It's going to have some OHs. Because it has lots of these, and it is a small molecule, it becomes very soluble in water. Vitamin A, on the other hand, has a very, very long nonpolar end. And vitamin A, instead of being soluble in water, is going to be soluble in fat. Pressure. Pressure affects mostly gases in water. So, for example, if you have a nice can of Coke, and our can of Coke, and we open up our can of Coke, we know that our bubbles are going to come out of our Coke. And we know the first thing that's going to happen is the CO2 is going to come off. So, why does that occur? Well, first of all, how do we get the CO2 in there? To get the CO2 in there, we put lots of carbon dioxide above our solution, our liquid here of Coke. As the pressure of that gas over the liquid goes up, so we have more and more carbon dioxide above our water, more and more carbon dioxide dissolves in the water. So this actually has a law involved, and it says that the amount of gas dissolved in the solution is directly proportional to the pressure of the gas above the solution. So we can do some math. So to reiterate, if you take and you have carbon dioxide in our soda, and you have the ability or the open bottle so that carbon dioxide can escape, the pressure out here is nice and low, and the gas is going to escape out of the liquid. Interesting occurrences on gases and liquids. Lake Nyos. Lake Nyos is in Cameroon, which is in Africa, and Lake Nyos is a big lake, and it is over a vent in the core. So here's our lake, and here's a vent in the mantle. A vent means that all of these gases, like the gases you would find from a volcano, can get into the lake. So what happens? These gases, for example, carbon dioxide, can get into the lake. So if CO2 gets in here at the bottom of the lake, well, why is this an issue? This is quite a ways down, at least 100 feet. If this is down at 100 feet, the pressure down here is very high. As the pressure down there goes up, the solubility of the carbon dioxide also goes up. So we dissolve lots of carbon dioxide down here. What happened? Well, what happened was that there was some sort of an earthquake or a landslide, we're not certain, and the lake itself was shaken. When that occurred, it was like opening the top of a soda, and the carbon dioxide came shooting out the top. When it did that, because carbon dioxide is very heavy, the carbon dioxide covered the landscape with CO2, which is very dense, and there were at least 1,700 people that were killed as they were smothered by the carbon dioxide. So what are we doing now? We have taken and put a vent in the bottom of the lake so that the carbon dioxide is going to bubble to the surface and get out, preventing this from happening again. So here's our equation. Our equation says the solubility of the gas is directly proportional to the pressure, and it's dependent upon a constant, which is our Henry's law constant. Henry's law constant depends on a lot of things. The case of H here depends on the gas, on the liquid, and on the temperature. So when we do this, it is only going to work for a certain gas in a certain liquid at a certain temperature. All right, so how many grams of ammonia will dissolve in 0.1 liters of solution given this partial pressure? The case of H has to be given as 0.58 moles per atmosphere. So we know that the solubility is going to equal 58 molar per atmosphere multiplied by the pressure. Well, this is in torr and that's in atmosphere. So let's recall that 7.6. Recall here that there are 760 torr in 1 atmosphere, so 760 torr, 1 atm, giving us 0.010 atmospheres. So if we multiply this by 0.010 atmospheres, this is going to give us 0.58 moles per liter, 0.58 moles per liter, multiplied by 0.1 liters, the volume of our solution here is going to give us 0.058 moles. And if we multiply that by the molar mass of ammonia, which is 17 grams per mole, we are going to get ourselves on the order of 0.99 grams of ammonia dissolved in 0.1 liters. So let's talk about a different case of this. Henry's law. Henry's law tells us that as the solubility of a gas is going to go up as the pressure of the gas goes up. So when will this occur? Well, let's imagine that we're scuba diving. If we're scuba diving, we know that we're underwater. So as we're underwater, we know the water is heavy. And because this is heavy, this is going to press on us, and this is going to increase the pressure. Well, as this happens, the air that is in our tank is going to actually physically dissolve in our blood. Not the oxygen, which is going to react, but the major component of air, which is nitrogen. Nitrogen is going to dissolve in our bloodstream. So what happens? More nitrogen dissolves. So as you go up, as you scuba dive, the pressure is going to decrease and this gas is going to come out of the body. As this gas comes out of the bloodstream, it tends to concentrate in the joints, in particularly in your spine and in your brain, and you actually get bubbles of nitrogen in the joints. As you get the bubbles of nitrogen in your joints, it is very painful, and you bend over in pain. It is called the bends, little bubbles of nitrogen in the joints. How do we fix this? We fix this two ways. One, we take and we go up slowly. If we go up slowly, we rise slowly as we scuba dive and we breathe carefully. We breathe the excess nitrogen off and it ceases to be a problem. If you're going to do deep diving on a regular basis, you are going to replace the nitrogen in your tank with helium. Why? Because helium is less soluble. Why is helium less soluble? It has lower dispersion forces. Like dissolves like. Lower dispersion forces. What about temperature? Now, temperature effects depends on whether or not we're looking at a solid dissolving into, for example, water, or we are looking at a gas dissolving in water. For a gas dissolving in water, our effect is always the same. As the temperature goes up, the solubility of the gas goes down. Gases are much more soluble in cold liquid. For most solids, as the temperature goes up, the solubility is going to go up. In most cases, sugar, for example, is significantly more soluble in hot water than it is in cold. Note that each of these curves has to be obtained experimentally. So if you were to do this, you'd have to get this. This is the saturation line. At this point, for example, at 20 degrees Celsius, this is the amount of sugar that is dissolved in 100 grams of water. If you're below here, your solution is unsaturated. You can dissolve more, and it's going to vary for every single different solid. For example, down here with the cesium sulfate, as the temperature goes down, the temperature goes down, as the temperature goes up, the solubility goes down. Gases, on the other hand, are consistent. As our temperature goes up, the solubility goes down. What does this mean? This means a lot of things. For example, if you want ocean water that has in it lots of oxygen so that it can support lots of plant life, which can support lots of animals, you need cold water. We know as the temperature goes up, the amount of dissolved oxygen goes down, and we have massive kills of fish, just for example, from hot water. For example, if your water gets too warm, so warm water becomes deoxygenated. Warm water becomes deoxygenated is called thermal pollution. And it doesn't matter if this is the ocean or if this is a lake in which warm water is being dumped into. If the dissolved oxygen goes out, fish can die, and we can have massive thermal pollution.